So, programming assignment 1 is going to be a game. Very simple command line based game that the computer is going to play with a user. And you're going to write programming assignment 1 using what we call shell scripting, so a bunch of Unix commands in a file. Program 2 is going to be the same assignment, but you're going to write it in C. Okay, so the first 2 out of 5 programs for this course, major programs, are this simple game that we're going to talk about now. And I want to describe the game and then talk about how you can implement a strategy to win this game if you're the computer. And then we're going to start working on developing an algorithm for this. And you're going to go back into groups today and you're going to do some brainstorming and kick around some ideas to come up with some high-level algorithms. And then tomorrow we'll work on actual flowchart. And once you've got that done, you're past the hardest part of your first 2 programming assignments. Right? At that point, you've got the steps that you need to perform, and it's going to be translating it into C and getting the syntax right, or translating it into a shell script. So this is actually, doing part of your first 2 large programming assignments. So the game we're playing is a game where you pick sticks from a pile. You start with a pile of matchsticks or toothpicks or something, and you take turns with each player picking either 1, 2, or 3 sticks. And the object of the game is to be the person who picks up the last stick from the pile. If you pick up the last stick, you win. So here's a typical example. So there's a bunch of sticks. And I'm going to play the computer and you're going to play the human, okay? And I'm going to let you go first. And you get to take either 1, 2, or 3 sticks. So how many sticks do you want to take? 3, okay. So we'll take off 3 sticks for you. And I'm going to take 1 stick. And it's your turn again. How many sticks do you want to take? So you're going to take 3 sticks, and well, I'm going to pair it also and take 1 stick. Now how many sticks do you want to take?
I don't want to take any.
You don't want to take any, right? But if you take 1, I'm going to take 3. If you take 2, I'll take 2. If you take 3, I'll take 1. And either way, I'm going to win. Okay? And then I can dance around and be happy. Okay, and there's an algorithm for guaranteeing that you always win this game most of the time. And the basic idea is, if I can get the game down to the place where it's your turn and there's only 4 sticks left, I've won. Right? This is the case we just had, because however many sticks you take, 1, 2, or 3, I can always pick up the last one. Okay, but if we have more than that, if I can get the game down to the point where there are exactly 8 sticks left, what can I do? I can guarantee that I can make this whole pile go away in the next turn. Because if you take 1, 2, or 3, I can pick up the remainder, and I can turn it into a game where there's exactly 4 sticks left. And we just saw if that's the case, I can win. And if we start off with 12 sticks, in 1 move, I can make this pile go away and turn this into a game where it's your turn and there's 8 sticks, and we just saw in that case I'm guaranteed to win. Okay, this is a bit of a recursive algorithm. 215, CSE 215, we'll talk about that. So the whole trick is trying to make sure that when it's your turn, the number of sticks left is a multiple of 4. Okay, so try to guarantee that on the user's turn, number of sticks left is divisible by 4. If I can do that, I can win every time. Now, to play this game and to make it fair, the user gets to set up the game. So the first 2 things your program wants to ask is, do you want to go first or should I go first? And how many sticks are we playing with? And the user gets to pick. So if you're the user and you understand this algorithm, how might you answer those questions to guarantee that you can win instead of the computer? So if you say, let's play with 4 sticks and you go first, then, so if I'm the user and I say, let's play with 4 sticks and you go first, I'm going to win, right? Because I just mimic the setup that our program is trying to mimic. But if there's 4 sticks and it's the computer's turn, they can't make a move that leaves a multiple of 4 sticks. Or if there's 8 sticks or 16 or anything like that. So I could always pick a multiple of 4 and say, you go first.
Or you could just always be the one that goes second.
Or I could be the one that goes second. But if I go second, is there a way that I can still win?
Well, yeah, because you just do whatever it is to make sure that throughout that turn, just 4 sticks or whatever.
Right, right. All right, so how do we think of this as an algorithm? When the computer is making its move, basically you want to try to satisfy this condition. And the only time you can't do this is if there's already a multiple of 4 sticks left. You could take 0 sticks, but that's illegal, right? So if there's a multiple of 4, any number of sticks I take, we're not going to be in this case. So one thing you can do is just take 1 stick and hope the user doesn't know what they're doing, and that eventually they won't leave a multiple of 4, and then you can put the game into this stage. Yeah?
Should we start with like number greater than divisible by 4? Greater than 5 sticks or something like that?
So what was the original part of that question?
Like start with the number like not divisible by 4?
So if you start with a number that's not divisible by 4, and you're going first, you can win, right? Because you can take off either 1, 2, or 3. But since we're letting the user decide how many sticks and who goes first, it's possible that they're going to be very clever and do exactly what you suggested, but in their favor instead. Okay, so got the basic idea, right? How to play this out, how to win. So here's what I want you to do. Go back to the board in groups, and let's spend, say 10 minutes. Let's go until 20 minutes till, and do some brainstorming. And I'm not going to suggest you go directly to a flowchart, because flowcharts make sense when you understand the algorithm perfectly. But when you're trying to figure out the algorithm, that's more when we talk about pseudocode. Okay, and pseudocode is really just kind of like a higher level description of what you want to do in each step. For example, pick a number of sticks so that the number left is divisible by 4, right? That might be something we put in pseudocode. Well, how do we do that? You got to look at the number of sticks. You got to do some division, some modular arithmetic with a percent sign, right? Whatever. Do some brainstorming, figure out the steps of this algorithm, and try to put together some pseudocode that basically says step by step what are we going to do. And take about 10 minutes to work on that. I'll walk around, I'll see what you're doing, ask you questions, and then we'll talk about that. We'll talk about some of the details of it, and then tomorrow we'll work on actually putting together a real flow chart for that, and that'll take us basically into PA1. Yeah?
So do you want us, the user, to go first, or the computer to go first?
The user gets to decide.
Okay.
So the program should say something to the effect of, do you want to go first or should I go first? And the user specifies that somehow. And then it says how many sticks should we play with, and the user can specify that. And then the game starts. All right, go ahead and do some brainstorming. All right, so what have we got here? We've got lots of algorithms. Pretty much, what's the first things that we want our algorithms to be doing? Very first steps. It's on pretty much all of these.
See if the player wants to go first.
Yeah, so get some input from the user. Figure out who's going first, how many sticks, right? And typically, not always, but typically from the highest level, a lot of programs break down into the following: input, processing, output, right? Not always. Sometimes you're outputting while you're processing, but a lot of times you get some information about how you're going to set up the system, you do a bunch of crunching, and then you generate some answer, right? And this is kind of like that, except we're inputting along the way with turns and so on. So this initialization, right, from user input and from variables and flags that we have is pretty typical in the beginning. And then what's the essential core of the gameplay? What's the main thing we're doing inside this loop that we keep running through until the game's over? What's the essential mechanics? Check to see if the number of sticks left is a multiple of 4. When do we want to check that? When it's the user's turn, right? So we're going to pick some number of sticks, and then we want it to be a multiple of 4 that's left. And hopefully, when they pick some sticks, it's not a multiple of 4, right? So that we can pick some number. And then a lot of groups figured out that if you simply see what the remainder is when you divide the number of sticks by 4, that's how many sticks you should take, right? So if there's 7 sticks, 7 divided by 4 has a remainder of 3. That's how many sticks you want to take. 7 minus 3 will leave you with a multiple of 4. And in C, I saw a lot of groups use the modulus function. That's exactly what the modulus does, right? So if you have some number n percent 4, that's the remainder of n divided by 4. All right, so the percent function is handy to figure out how many sticks do we take so that we end up with a multiple of 4. So you can use that directly in your algorithms. Previous section, I don't think anybody picked up on this. A few groups picked up on this now. What if the user says, I want to take 17 sticks? And you started with 17 sticks and the user wins. Right? Or they say, I want to take 0 sticks. Or they want to take -2 sticks to add some more sticks into the game, right? Is that kosher? Probably not, right? So I like to imagine when I'm writing code that instead of a human user on the other side, it might be like a dog, right? Sniffing around on the keyboard and hitting keys randomly. And what's your program going to do in that context, right? Hopefully it's not going to blow up. So what are some of the things we want to make sure when we say how many sticks should we play with? It's got to be an integer. It's definitely got to be bigger than 0. It's probably got to be bigger than something, right? If they say, I want to play with 2 sticks and I'm going first, you don't have much of a chance of winning, right? So you might want to say, pick at least 10 sticks, right? Just to make it interesting. And it's got to be a bunch of digits, right? So it's a legal integer. It can't just be random keystrokes like the dog would do. And same thing when you say, how many sticks do you want to take now? It's got to be an int. It's got to be bigger than or equal to 1 and less than or equal to 3. So this is sometimes called defensive programming, right? You always want to make sure that you're not assuming the user knows exactly what they're doing, right? They might type in something crazy, and this is where a lot of exploits come from, right? You build a system and you ask for the username and you assume, well, nobody's going to have a username that's 10,000 characters long. Yeah, they are. And when they type it in, they're going to take over your system because you didn't code for that case. So you always want this defensive programming. You want to make sure that you're checking the inputs and making sure they're reasonable before you just throw it into the code and say something like, okay, so take this thing that's not a number and divide it by 4 and your code blows up. So we're going to want to think about that when we're actually doing these longer term programming assignments. And how do we deal with that, right? Just throw in some more conditionals, right? So a diamond, if I is less than 1, then, you know, you could exit, you could print a message saying, hey, you got to pick between 1 and 3, and then go back up to the input section, and so on. And again, if you're working at the level of a flowchart or pseudocode, it's really easy to put those things in, right? If you're working at the level of C program, you got to somehow kind of reverse engineer that in your brain or look at the well-written comments you've put in your program to figure out where you need to make those changes. And editing a C program can be a little error-prone sometimes. You can introduce glitches while you're trying to add features. So again, if you take a problem you're trying to solve and you start thinking of it in terms of what are the steps, what's the algorithm, what's the flow chart, right? Once you understand this, convert it into C or shell scripts or whatever, and keep this next to you, right? So that when you're debugging your program and it's not doing what you want, you can come through here and say, well, here I should be checking if R is bigger than 0 and do this. and it's not happening, and you can look in your code and say, oh, I know what I did, right? Did you have a question, or you're stretching? Okay. All right, so we're out of time here. So tomorrow I want to start looking at some shell scripting. So ways that we can actually write commands in the Unix shell to let us do some of these things and write a program. And then we're going to go and we're going to try to turn what we've done here into full legitimate flowcharts, okay, that we could eventually turn directly into a program. All right, so I'll see you there.